let us discuss what we studied in the previous class. So previous class we started the subthreshold leakage current. So the various factor which involves in the subthreshold leakage current. The factors are like double, that is drain induced barrier leveling, the body effect, the narrow gate width effect, then VTH roll off, then the temperature effect, then tunneling through gate oxide, then hot carrier injection, then a gate induced drain leakage. Until that we studied in the previous class. So now let us concentrate on the next mechanism of subthreshold leakage current is punch through, or I can call it as channel punch through, or this sometimes we may call it as channel punch through. Sometimes we may tell like this. Okay, so let us consider the diagram, so it will be more easy to explain. So this will be your then this is your silicon dioxide, this will be your silicon dioxide layer, the terminal, then we have the N plus region, here also N plus region, then this will be your bulk, this is P-type P substrate, source, drain. Okay, now what will happen? In the short channel devices, due to the channel is less, the length of the channel is less, so the drain and the source region is right. So what will happen? The depletion region at the source and the depletion region, the source and the substrate, this one. Okay, the depletion region, source and the substrate, and the drain and the substrate will be extended into the channel. So how it will be extended? In the sense, it will be extended like this. The first it will be like this. This is our depletion region. Okay, then we'll get like this, then it will go like this. So now your depletion region will be like this. See what will happen? Your depletion region will be extended. So because if I take a complete diagram, you will have the depletion region is like this. See, it will be extended into the channel. So but if the doping, if you are keeping the doping as constant while the channel length is reduced, then the separation between the depletion region boundary will be reduces. Which one? This one, which will get reduces. So you need to increase the reverse bias. So how you can increase the reverse bias? Make it VDS as higher. The junction further decreases the separation if you make VDS is larger enough. When the depletion region is merged, so now do you think like this one? See, like this. Okay, so when the depletion region gets merged, then the majority carriers of the source, which one from here, the majority carriers of the source will enter into the substrate. Then from the substrate, the and get collected by the drain actually. So that situation only we can call as punch through condition. So now simple I can say. So due to the proximity, of the drain on the source and the short channel devices, the depletion region at the source and the substrate. I will write substrate as bulk, okay? Substrate and drain and substrate, D and P. Both the junctions will be extended into the channel. So you can see here the net effect of the punch through this one increases in the subthreshold current. So increases in the subthreshold current. So moreover, what it will do, the punch through degrades the subthreshold slope. Next, the punch through voltage so that will be denoted as VPT. That will estimates the value of VDS. That's for which punch through occurs at VGS is equal to 0. Punch through occurs at VGS will be equal to 0. So what is the equation? The punch through voltage is directly proportional to NB into L minus Wj. So the punch through will be depends on these parameters. What is the parameter? The first parameter is which one? That NB. NB is nothing but the doping concentration, because already we said you need to keep constant doping. So doping concentration of the bulk actually. You see. Next, L. L is nothing but channel length. Then Wj. Wj is nothing but the junction width. So these three parameters which affects or which will give the punch through voltage actually. So now what we can do, let us go for, we'll summarize all the leakage power dissipations. So when I give the summarize, we can see here the graph which is showing is the N channel drain current versus the gate voltage. So this will be your gate voltage, this is your drain current, which illustrating the various leakage components. Here you can see the various components. So like the first one is like for various VD value. So here this one is will be VD is equal to 0.1. So this will be your 2.7. This will be drain voltage 4. So gradually we are increasing the VD, that is drain voltage. When I increase the drain voltage, or you can keep, right? So just increase the drain voltage. Now the gate voltage increases over there. As you know, this is right. So you can see here we are having the dibble. So drain induced barrier lowering will happen over in this place. See, between this portion 0. Sorry, not between that place. See, exactly. Drain will be induced. Then you can see GIDL, that is gate induced drain leakage will happen. What happens, like when the Vg is equal to 0 or less than Vg is negative value, then we are having this. You can see. So your ID is getting reducing over there. Then we are having the junction leakage also. So with this effect, what I can say in the sense, you can see the one more thing we are showing here, like this will be your technology, correct? The technology which is like gradually is improvising, means technology is reducing 130 nanometer, 100 nanometer, 65 nanometer, next to 45 nanometer, keep on. Okay, you see which is showing the colors here. This one which shows the subthreshold leakage from the source. So this one will be a gate induced drain leakage current. Then this will be a junction reverse bias leakage. Then the last one, the gray color, shows the gate leakage direct tunneling. You can see the 130 nanometer. If you see, the gate leakage tunneling will be around like 10%. Example. Okay. The rest of the things are will be 30%. You can see. So this leakage, the junction reverse bias will be 30%, gate induced leakage around 30%, then subthreshold leakage also will be around 30% in the 130 nanometer. Now what happened? Your length gets reduces, that is the short channel, right? When you go for 100 nanometer, what happened here? When you reduce the length, the gate leakage, we are getting around 40%, we are getting gate leakage, that is a direct tunneling, because if you reduce the length, automatically your the the oxide thickness will be very thin. What will happen? There will be a direct tunneling, that is a gate leakage will be there, that is giving more actually. The junction reverse bias will be very less. You can see this around 10% maybe will be there. This also will be around 10%. This is almost again this also I can say 40%. Subthreshold leakage from the source. So the subthreshold leakage from the source current and the leakage current will be more in the 100 nanometer. But now you see 65 nanometer, what happened here? Again the gate leakage is become 90%. I can say 95% is gate leakage only. That is a direct tunnel. But you can see the very small amount of like the junction leakage will be there, then gate induced drain leakage, then you can see subthreshold. Now keep on you increase, like say example 45 nanometer also, then if you keep on, if you increase the, and means you are reducing the channel length, then your gate leakage will be more. So that is what when you do in this, we are saying for various power dissipation here, as the length, like for various sources of power dissipation, like because various sources of power dissipation already we said, in that which one will have the major contribution. If I am saying, then the major contribution will be like the switching power. You can see this, the switching power, that dissipation will be around 80%. 80 to 90% will be switching power. Then the leakage power will be around 10 to 30 power only. Short circuit power will happen only 5%. Then the static power will be 5 to 10%. So the more will be the switching power only will get, because during the device is active in condition. So at that time the switching power will happen. So but the leakage power, when it will happen, leakage power when the circuit is in inactive mode, the short circuit power also will be like when if both the transistors are on. It's very rare case actually. Then static power. So we can say uh, if you are for finally what you need to do when you are going for the average power, in the sense if you want to calculate the average power, finally if you are calculating, then that will be the summation of, what is a summation of switching power plus leakage power plus short circuit power plus static power. So this only will give the overall the average power dissipation. So it will be like, as we know that by short, you know the formula how we can write the summation of PSP, switching power dissipation, right? Switching power dissipation, PS plus power leakage power, then short circuit power, then static power. Like so, as you know the formula how we can do for switching, actually it will be like this. So alpha CL into VDD square into F clock. This will be your switching power. Then for leakage power, ISC into VDD. Then plus not leakage. This is a short circuit, right? Then this will be I leakage dot VDD, the current into VDD. Then I static into VDD. See, so you need to calculate individually. So this factor, no? Which factor? We are having this. This is the alpha is nothing but switching activity factor. So now from this, if I say the degrees of freedom, if I say freedom means which will be the hierarchy wise, which is the major factor to contribute for the leakage power in the sense, you can say the first one will be supply voltage. So to reduce the leakage or which is the contribution, first is supply voltage. We need to reduce the supply voltage. You can see here all the things you can see VDD, 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 VDD. If I reduce the VDD, automatically the average power, the dissipation will get reduced. So that is the first factor I can say. The second factor is nothing but it's a physical capacitance. So that is nothing but what the internal node capacitance and the load capacitance. So that we need to reduce. That is what means this one, physical capacitance. Right? So next is nothing but switching activity. That is, so that we have to can reduce that. Next finally is nothing but threshold voltage. So these are the four parameters. Now you can see here when change in the active and standby power, the change in the technology here. You can see the technology which is going here in terms of micrometer, 1 micrometer, 0.8 micrometer, 6, so 0.18 micrometer, that is nothing but 180 nanometer. So here you can see the power, like how it is changing the active and the standby power, changing the technology. You can see this as for 0.8 for 1, the standby power will be 10 to the power minus 4 watts, but for active power is 10 to the power 0. As the technology means as the length of the channel get reduces, so what has happened? The standby power is getting increases, but the active power is not increasing. The stand power is exponentially, it is increasing. So this is about the sources of power dissipation. So in this we seen all the factors, which are the factors are which involving for the power dissipation.